Now that we've spent a couple of videos exploring a scenario where I'm taking multiple free throws and figuring out the probability of making k of the scores in 6 attempts or in n attempts, let's actually define a random variable using this scenario and see if we can construct its probability distribution. And we'll actually see that it's a binomial distribution. So let's define the random variable x. So let's say that x is equal to the number of made shots, number of made free throws when taking 6 free throws. So it's how many of the 6 do you make? And we're going to assume what we assumed in the first video in this series of these making free throws. So we're going to assume the 70% free throw probability right over here. So assuming 70% free throw percentage. All right. So let's figure out the probabilities of the different values that x could actually take on. So let's see. What is the probability? What is the probability that x is equal to 0? That even though you have a 70% free throw percentage, that you make none of the shots. And actually, you could calculate this through probably some common sense without using all of these fancy things. But just to make things consistent, I'm going to write it out. So it's going to be equal to 6 choose 0 times 0.7 to the 0th power times 0.3 to the 6th power. And this right over here is going to end up being 1. This over here is going to end up being 1. And so you're just going to be left with 0.3 to the 6th power. And I calculated it ahead of time. So if we just round to the nearest, if we round our percentages to the nearest tenth, this is going to give you approximately, well, if we round the decimal to the nearest thousandth, you're going to get something like that, which is approximately equal to 0.1% chance of you missing all of them. So, roughly, I'm speaking roughly here, 1 in a thousand chance of that happening, of missing all 6 free throws. Now let's keep going. This is fun. So what is the probability that our random variable is equal to 1? Well, this is going to be 6 choose 1 times 0.7 to the first power times 0.3 to the 6 minus first power, so it's the 5th power, and I calculated this, and this is approximately 0.01, or we could say 1%. So still a fairly low probability, 10 times more likely than this, roughly, but still a fairly low probability. Let's keep going. So the probability that x is equal to 2, well, that's what our first video was, essentially. So this is going to be 6 choose 2 times 0.7 squared times 0.3 to the 4th power. And we saw that this is approximately going to be 0.06, or we could say 6%. And obviously, you could type these things in a calculator and get a much more precise answer, but just for the sake of just getting a sense of what these probabilities look like, that's why I'm giving these rough estimates. Kind of, I guess you could say to the closest maybe tenth of a percent. And actually, even if you round to the closest tenth of a percent, you actually get to 6.0%, and this is 1.0%, because we actually went to a tenth of a percent here. But let's keep going. We're obviously going to have to do a few more of these. So let me just make sure I have enough real estate. All right. So the probability that our random variable is equal to 3 is going to be 6 choose 3. And I'm sure you could probably fill this out on your own, but I'm going to do it. 0.7 to the 3rd power times 0.3 to the 6 minus 3, which is the 3rd power, which is approximately equal to, well, it's going to be 0.185 or 18.5%. So yeah, that's definitely within the realm of possibility. I mean, all of these are in the realm of possibility, but it's starting to be a non-insignificant probability. So now let's do the probability that our random variable is equal to 4. Well, this is going to be 6 choose 4 times 0.7 to the 4th power times 0.3 to the 6 minus 4, or second power, which is equal to, this is going to get equal to, or approximately, because I am taking away a little bit of the precision when I write these things down, 0.324, so approximately 32.4% chance of making exactly 4 out of the 6 free throws. All right, 2 more to go. Let's see, I have not used purple as yet. So the probability that our random variable is equal to 5, it's going to be 6 choose 5, or 0 times, I should say, 0.7 to the 5th power times 0.3 to the 1st power, and that is going to be roughly 0.303, which is 30.3%. That's interesting. One more left. So the probability that I make all of them, of all 6, is going to be equal to 6 choose 6, and 0.7 to the 6th power times 0.3 to the 0th power, which is this right over here is going to be 1. This is going to be 1, so it's really just 0.7 to the 6th power, and this is approximately 0.118. I calculated that ahead of time, which is 11.8%. And so there's something interesting that's going on here. The first time we looked at the binomial distribution, we said, hey, there's this symmetry as we kind of got to some type of a peak and went down, but I don't see that symmetry here. And the reason why you're not seeing that symmetry is that you are more likely to make a free throw than not. So you have a 70% free throw probability. This is no longer just flipping a fair coin. Where you will see the symmetry is in these coefficients. If you calculate these coefficients, 6 choose 0 is 1, 6 choose 6 is 1. You would see that 6 choose 1 is 6, and 6 choose 5 is 6. You'd see 6 choose 2 is 15, and 6 choose 4 is also 15, and then 6 choose 3 is 20. So you definitely see the symmetry in the coefficients, but then these things are weighted by the fact that you're more likely to make something than miss something. If these were both 0.5, then you would also see the symmetry right over here. And you can plot this to essentially visualize what the probability distribution looks like for this example. And I encourage you to do that, to take these different cases, just like we did in that first example with the fair coin, and plot these. But this essentially does give you the probability distribution for the random variable in question. This is, I just wrote it out instead of just visualizing it. But it says, okay, well, these are the different values that this random variable can take on. It can't take on -1, or it can't be 15.5 or pi or 1 million. These are the only 7 values that this random variable can take on. And I've just given you the probabilities, or I guess you could say the rough probabilities, of the random variable taking on each of those 7 values.